In this lecture, we are going to talk about laws of Boolean algebra. But before we formally begin, let's have a short background of what a Boolean algebra is. Boolean algebra was introduced by George Boole. He is an English mathematician, a philosopher, and a logician. His contribution was widely used in the design and analysis of digital electronics, computer programming, and statistics. Boolean algebra has three operations. Number one is the AND, or also known as conjunction. Number two is the or disjunction. And the last is the NOT, or negation. Boolean algebra operates on values 1 and 0. 1 stands for true and 0 for false. Let's take a look on how the AND operation works. Let's say we have variable A and B for our input, and then we AND A and B. Suppose the input for A is 0 and 0 for B, and we get 0. As you observe each row, as long as there is an input of 0, the result is 0. We can only obtain a result of 1 if both inputs are 1. The OR operation works oppositely as the AND operation. Observe the second row, third row, and the last row. As long as there is an input of 1, either for A or B, we get a result of 1. The only time that we can get 0 if both inputs for A and B are 0. For NOT, it takes a single variable or expression. Suppose we have an input 0 and we NOT or negate the 0, it turns 0 to 1. And suppose we have an input of 1, then we negate 1, then it becomes 0. So I hope that you're getting the idea. You are just inverting the value of the number. So this is the complete list of the laws of Boolean algebra, a total of 17. We will discuss each of these by proving that each equation is true. Let's take a look at the first law of Boolean algebra, the annulment law. The annulment law states that regardless of the value of A, as long as there is a constant, the answer is the same as the constant. So these are both true for OR and AND. So let's take an example of this. It's said to be that A plus 1 is always 1. It is because if we set our A to 0 and add it to 1, the result is 1. If we set our A to 1, then added with 1, still the result is 1. Regardless of the value of A, as long as the constant is 1, the answer will always become 1. Let's take the second annulment law. It is said to be that A and 0 is 0. So suppose the value of A is 0 and it with 0, then obviously this becomes 0. And let's say the value of A is 1 and it with 0, and still the answer is 0. So as long as there is 0 with AND, the answer will become 0. So the constant is always the answer. regardless of the value of A. The identity law works oppositely with annulment law. The identity law states that regardless of the value of the constant, the answer will be the same as the value of A. So we have the constant, but the answer is the same as the variable A. So let's take this example. A plus 0 is said to be A. So let's say our A is a value of 0, then we add 0 to it, still the answer is 0. So A is 0 and the answer is 0, so meaning A is A. Let's do the same thing if the input is 1. Then add it with 0 and then the answer is 1. So A is 1 and the answer is 1, so A is equals to A. So this proves that regardless of the constant, the answer will be the same as the variable itself. Let's take the second identity law. A times 1 is said to be A. So if A is said to be 0, then we AND it with 1, then the answer is 0. So remember, A is 0, then we get 0, so therefore A is equals to A. If we set A to contain 1, AND it to 1, then we get 1. And again, A is 1, and the answer is also 1, so it means that A is equals to the answer. This proves that regardless of the constant, the answer will be the same as the variable itself. Let's move to idempotent law. It is said to be that A plus A is equals to A. So let's prove this. A plus A is equals to A. Suppose our A is 0. We added with the value of 0 because A is 0. So the answer is still 0. So let's say the value of our A is 1. Then we added 1. Then our answer will become 1. So if both inputs contains the same value, adding them together will be the same as the input. That is the idempotent. This is also true for the AND operation. So let's say we have this A times A is A. So we set A to 0, and it to 0, and it is still 0. If our A is 1, we add it to 1, then it is 1. If both inputs contain the same value, then the answer is the same as the input itself. Okay, so we are through with this. Let's take the complement law. A plus A negated is 1. So A is 0, then we negate A, this becomes 1, then 0 plus 1 is 1. If we set our A to 1, we negate the value 1, becomes 0, so this becomes 1. So this is why no matter what will be the value for our A, if we negate the variable itself, then the answer will become 1. So the same goes with the AND operation. Now let's take a look at the double negation. So if you have A and then we negate A and then negating it again, will always result to A itself. So let's discuss what do we mean by this. If we set our a to 0, we negate a, this becomes 1, and then negating it again, this becomes 0. So it goes back to its original form. The same thing happens when the input is 1. It becomes 0, then it turns back to 1 again. So therefore, double negation is the same as the original form of the variable itself. Okay, let's move to the associativity. Let's take a look on the first associativity. So this law is the same as the law that you had on the secondary algebra. It states that no matter how we group our expression, as long as they are all same in the operation, the result is still the same. So example, 1 plus 2 plus 3, if we group this would result to 6. And if we change the grouping, 1 plus 2 plus 3, we change the grouping, and the answer will still be 6. So no matter how we group our expression, as long as the operation are uniform, so the result will not change. So the same effect applies to the AND operation. Now let's take a look at the commutative law. Commutative law states that no matter how we order or rearrange our inputs, let's say 1 plus 2 is the same as 2 plus 1. Or let's say 3 times 2 is the same as 2 times 3. So that is the commutative. For absorptive, this works differently. So let's discuss the first absorptive. So we have A plus A times B is A. And actually we can rewrite this to something shorter like A plus A times B is A. So we can work on this. What we will do is to factor out the similar literals. And we can do this by stating that A times 1 plus B equals to A. And it is said that no matter what the value of our variable, as long as there is a constant, this always results to 1. Okay? So A times 1 is A. And A times 1 is always A. Therefore, A is equals to A. So this is absorptive. Let's take a look on the second absorptive. So A times A plus B is said to be equals to A. Now we can write this as if A times A plus B is A. Now we can apply distributive here. So A times A plus A times B. So we distribute this literal to each term inside of our parentheses. And A, this is just A. Then we apply factorization. This becomes A. And this one becomes just 1. And A times 1 is A. It's equals to A. This solution clearly states that the absorptive equations are true. Okay, now let's take a look at the DeMorgan. Let's start with the first DeMorgan law. We can prove this by plotting a truth table. So suppose we have an input A and B, and then we negate them, and then we combine them as one expression but negated. So suppose the input for A are the following values: 0, 0, 1, and 1, and then for B is 0, 1, and 0, 1. And we negate the value of A, this becomes 1, 1, 0, 0. And we negate the value of B, this becomes 1, 0, 1, 0. And then we multiply or we AND A and B, and then we negate them together. For this column, we will AND the A and B, and then we will negate the result. A and B, this becomes 0, and then we negate it, then it turns to 1. 0 and 1 is 0, we negate it, then it turns to 1. 1 and 0, still that is 0, then we negate it, it becomes 1. 1 and 1 becomes 1, then we negate it, it becomes 0. Now for the final equation. So we have to add here A plus B, and A is negated and as well as B. So in this column, what we will do is to add the negated A and negated B, or the not A and not B. So we have to OR them or add them together. So not A plus not B, this is 1. Not A plus not B, 1. Not A plus not B, this is 1. And not A plus not B, 0. So as you can see here, these columns are equal. They contain the same values, which clearly shows that this expression is really equal to this expression. So the same thing applies with the second DeMorgan law. So you can check it out by creating or plotting a truth table similar to what we did in this solution. So that's all for the laws of Boolean algebra, and I hope that each of these equation is clear to you. See you in the next videos.